Spontaneous processes occur without outside intervention. They can occur fast or slow. You need kinetic data to determine the speed of the reactions. So again, speed has to do with kinetics. Carbon spontaneously turns into diamond, but that's a very slow process, but a spontaneous process. This lesson has to do with entropy. Entropy is represented with the letter S, and it basically represents disorder. The driving force for a spontaneous reaction is an increase in entropy. Kind of like this guy's office, if you just go to your room every day, leave for school, your room over time gets dirty. You get dust on it, clothes just magically wind up on the floor. Your room goes towards more disorder. You have to put effort into it to clean your room. Same thing. The room spontaneously gets dirty. So entropy is S, and you can think of it as the measure of disorder of a reaction. We measure it with positional entropy. So the probability of occurrence of a particular state depends on the number of ways, which are referred to as microstates, in which that arrangement can be achieved. Solids have the lowest positional entropy because there's only so many places in a container that a solid can be because it's only vibrating. Liquids have more positional entropy. They're flowing past each other. And then gases have the most positional entropy because they completely fill the container. So gases have way more positional entropy than solids and liquids. Here we can see some of those microstates. On the left-hand side, we have 4 particles, and there's 5 different arrangements that those 5 particles could be in. I could have 4 on the left, I could have 3 on the left and 1 on the right. I can have them equally halved. I can have 3 on the right, 1 on the left, or 4 on the right, none on the left. So 4 particles, I have 5 arrangements, but if I only have 2 particles, I only have 3 arrangements. So the fewer the particles I have, the fewer microstates I have, therefore I have less entropy. So this one is more entropy, this one is less entropy. So when referring to entropy, we're talking the number of microstates that a system can achieve due to the states of matter, the number of particles, or also the volume/pressure. The higher the positional probability, the larger the entropy, more S or positive S. Increasing going from a solid to a liquid to a gas, which we saw a few slides ago. And it increases when you have a larger volume. So small volume, large volume. This one would have a larger S. If I have a lower pressure, then that often refers to a larger volume. So lower pressure or larger volume will increase the positional entropy or positional probability, which is entropy. You'll see some problems like this where you just need to decide who has a higher positional entropy, in other words, who has more disorder, a solid or a gas. If you said gas, you are correct. Go ahead and pause the video and do B. We have high pressure and then a low pressure. So if you said low pressure, you are correct. So higher positional entropy equals more microstates. So go ahead and predict the sign of entropy change. So it's going to be positive if we have an increase in entropy, and negative if we have a decrease in entropy. So read the sentence and depending on what's happening in the scenario, figure out if there's more disorder or less disorder. So in this case, we're going from a solid sugar plus liquid water to make an aqueous solution. That is an increase in disorder, because we had a solid and a liquid and they were separated, and now they're going to be mixed together. So an increase in disorder. Sometimes in an ionic system, it actually becomes more ordered when you mix them. But in general, we're going to say that when you make a solution, it's going to increase disorder. We have a vapor, condensing. So we're going from gas to liquid. So that one you should have said a negative disorder or a decrease in entropy. Go ahead and pause the video and figure out the answer to this one. Figure out what's happening on each of them. Restart when you're done. So freezing is going from a liquid to a solid. So that's decreasing entropy. Melting is going from a solid to a liquid. So that is increasing disorder. Evaporating is liquid to gas. So that's increasing disorder. An expanding gas is going from a small container to a big container, so that's an increase in disorder. So A. D is an increase in disorder because, again, if I had two molecules of gas, they have much more microstates in the container to the right. Go ahead and pause the video and figure out which one has the highest entropy. So the one with the largest volume would have the highest total entropy because it would have the greatest amount of microstates like we saw in that last problem. So A was the correct answer. When you have a chemical reaction, the change in positional entropy is dominated by the relative number of molecules of gaseous reactants and products. So we're going to add the moles of gas reactants and the moles of gas products and see which one is more. So for example, these we're seeing, do they have an increase or decrease in entropy? Remember that I would only be looking at the moles of gas. In this case, all of these are gas, but I have a 1 and a 3, so I have 4 moles of gas going to 2 moles of gas. Well, that's a decrease in disorder, or a negative delta S. Go ahead and pause the video and do number 2 and 3 on your own. Restart when you're done. So for this next one, I have 1 to 2. So that's an increase or a positive delta S. And the last one, you had 4 and 5, so that's a 9. Going to 4 and 6 or a 10. So that's also an increase or a positive delta S. If this, let's say, was liquid water, then I would have 9 to 4 because I wouldn't care about that 6 liquid, and then it would have had a decrease in entropy. But again, in this problem, it was a gas, so we just went from 9 to 10. Here's 2 more. Go ahead and pause the video and figure out your sign of delta S. So figure out if it's a positive or negative. Restart when you're done. This one is similar to the one I was talking about previously. We have a solid, so we have 0 gas going to a solid and a gas, so 1 mole of gas. So that's a positive delta S. Make sure that you're looking only at the gas. You could have gotten it by saying 1 to 2, but that would have been incorrect. If you were explaining it on the AP test, you would say that the system went from 0 moles of gas to 1 mole of gas, which is an increase in positional entropy, or an increase in the number of microstates. For B, we had 2 plus 1, so 3 moles of gas, to 2 moles of gas, so that's a decrease or negative delta S. The second law of thermodynamics states that in any spontaneous process, there is always an increase in entropy of the system. The third law of thermodynamics says the entropy of a perfect crystal at 0 Kelvin, which was absolute zero, where all motion stops, is 0. In other words, everything has entropy. We can get those entropy values from an appendix of a book, or in the back of your notes, we also have that thermodynamics table that was taken from an index of a book, where we can get the S naughts for a compound. So our equation is delta S naught of a reaction is equal to the sum of the moles of the products minus the sum of the moles of the reactants. So remember that this symbol stood for sum, and then N is for moles. We're solving just like we solved for delta H. We have a table just like delta H, but unlike delta H, oxygen would have been a 0 delta H of formation because elements and diatomics aren't formed, so they don't have heats of formation or enthalpy values. But delta S, everything has entropy, so we have values for everything. Another thing to make notice that our gases have much higher disorder values than our solids do, because gases have more positional entropy. So just like before, we're going to do products minus reactants. So delta S is equal to open bracket. I have 2 sulfur dioxide, so 2, and then sulfur dioxide is 248 plus, so this was SO2. We have 2 nickel oxides, which are 38, close bracket, minus, I have 2 nickel sulfides at 53, plus, so that was nickel sulfide, 3 oxygens at 205. I would suggest doing all of your products. So again, this is products minus reactants. Delta S equals. So my products are 2 times 248 plus 2 times 38, giving me 572 minus, and then my reactants, 2 times 53 plus 3 times 205 is 721. Subtracting that, I get negative 149 joules times moles times Kelvin, which are the units of the table. We could have also predicted that this problem would have a decrease in entropy because I went from 3 moles of gas to 2 moles of gas. Okay, go ahead and pause the video and try this one on your own. Restart when you're done. This one would have been a harder one to predict if delta S is positive or negative because we went from 3 moles of gas to 3 moles of gas. So we really need this data. We do have 1 solid and 2 solids, but that's not always going to hold true like the gases are. So we have to actually calculate the entropy to figure out if this is an increase or decrease. So for your work, you should have had 2 times 28 plus 3 times 189. All of that gives you 623 minus 51 plus 3 times 131. All of that is equal to 444. Therefore, my delta S is 179, and that's joules per mole times Kelvin. Sometimes it's understood to be per mole, and so you'll just see joules over Kelvin, but most of the time it's going to be joules per mole times Kelvin. You can also solve for entropy using Hess's law, just like we did for enthalpy. Remember with Hess's law, you manipulate the equations that you know the delta S for, or delta H for, or whatever we have, to make it add up to the equation given that you're trying to find the delta S for. If you reverse a reaction, so if you reverse, you're going to change the sign. So from positive to negative. If you multiply the reaction, you're going to multiply the delta S. If you divide the reaction, then you're going to divide the delta S. So those are your basic principles. Whenever you're done, you just add up all of your delta S values. So let's look at this one. We are trying to get that top equation. So I'm going to look and try to find iron solid. Well, I have iron solid here. It's a reactant. It's the correct number, so I'm going to circle it saying that this one is good. Then I try to find my 5 COs, which are also right here. Correct location, correct number. And then I want FeOCO5 gas. Make sure you're paying close attention to the state symbols when you have more than one state symbol type. In this case, I had liquid and gas. It's a product. It's already in the right location, right number. So everything is where it should be, and then things on opposite sides cross out. Things that are on the same side add together. So everything is in the correct spot, so all I need to do is add my delta S values up. When doing so, I get negative 570.1 joules times Kelvin. Remember that technically it is joules / mole Kelvin, but I'm going to go with whatever units are given to me in the problem. I could predict that this was a negative delta S because I went from 5 moles of gas to 0 moles of gas. That's a large decrease in disorder, so I would expect to have a negative delta S, which I do.